Hi everybody, it's John Myatt from Imagine Communications, and today we're talking about NMOS. Now, NMOS is a critical part of a SMPTE 2110 system. And as you know, SMPTE 2110 is broken into a lot of documents that define uncompressed video and uncompressed audio and AES-3 emulation and all kinds of streams that go on a network. But you might have wondered, how do I know, or how does a control system know what all these streams are? That's where NMOS comes in. So in 2110, we talk about these session description protocol packets, and they're defined in an IETF document, RFC 4566, and they're all the data, all the stuff you need to know to use a stream. And it doesn't matter if it's a video stream, an audio stream, they all have this SDP. Well, all 2110 says is you should make an SDP and here's how, but it doesn't say what to do with them. But the preferred way in 2110 systems is to use AMWA NMOS to deal with these SDPs. And so the AMWA NMOS protocols are how a controller gets that information from senders and how it conveys it into receivers. Couldn't be simpler, right? But here we go. What's an SDP look like? It looks like this. It's got all these lines of text. It's human readable to a human who's used to reading this sort of thing. But for the rest of us, there's summaries. Now, 2110, as I mentioned, is all about transport, all about what's on the wire. The control is a different matter because in SDI routing, control happens inside the router. This big cross point, and the control system tells the cross point to switch these signals. The receivers just sit there and eat what shows up. But in IP, it's completely different. In IP, the receiver's involved in the process. The receiver is part of the connection. And so the receiver actually has to know not just what stream to ask for from the network, but also technical metadata that goes with that stream. How big is it? What HDR format is it in? Important things like that. So it's a little different. Now, when you're building a system, obviously you need a lot of details, and there's big spreadsheets full of details, and maybe sometimes vendors have automated discovery, and most vendors like us, we can discover our own equipment. But when you have a lot of stuff from a lot of people, it can be really tedious. So you'd think in IP, how's it going to work? Well, the sad part is it could be harder, right? And so the whole notion is that we wanted to have, as an industry, a standard protocol for finding the devices, finding the parts, and also some kind of universal driver for telling a device to switch streams and what stream to switch to. That's what AMWA NMOS is for. So that's the whole purpose of NMOS, is to be that discovery mechanism for devices and the how do you switch streams. Now, people talk about open, and this word open is used a lot of ways. AMWA NMOS is free. The spec is free. It's public. You can go on GitHub and download it, and there's the URL. Likewise, there's a couple of open source implementations of some of the parts of the system. Now, like all open source tools, they are what they are, and they work like they work, but at least they're interesting to play with to get your feet wet. So there's two critical parts to NMOS. There's ISO 4 and ISO 5. So first, we'll talk about ISO 4. ISO 4 is how, if you make a media node, so it's a thing that's got senders or receivers inside it, how do you start up? So the media node looks in DNS, the same way your browser finds Google is how the media node finds the registry. It finds this thing called the registry, and it pushes into the registry some information about who it is, what it can do, what streams it has. And then it also keeps the registry current if there's anything that changes. So if a camera changes from SDR to HDR, for example, the sender associated with that camera pushes an update to the registry saying, hey, that changed. Then controllers, things like our SDNO control system, other people's controllers, what have you, can query the registry to find out what's current. And they can also subscribe to updates. So anytime something changes on the registry, they find out about it straight away. Now, this is a really powerful concept because That means I didn't have to go to every camera and tell it how to connect to the control system. Instead, the camera woke up, looked up where the registry is, and connected all on its own. And then the control system can query the registry and say, oh, look, a new camera. It's a big deal. So what's in this magic registry? Well, the registry is composed of nodes. So every, say, production switcher might be a node, or a camera control unit might be a node. It's just a node is a collection of some things. Inside the node are what we call devices, and inside devices are senders and receivers. So senders send streams into the network. Simple, right? Receivers receive streams from the network. Again, not that complicated. And then there's some other stuff called flows and sources, and we'll talk about flows and sources later after we go through the easy stuff. So if you actually look in the registry, what do you get? Well, you get this big blob of JSON encoded text. And is that human readable? Well, again, for the right human, it's sort of readable, but it's not meant to be a human presentation, right? This is a machine-to-machine control interface. So the nice thing is these are implemented using HTTP, the same thing your web browser uses. So you can actually point your web browser at the NMOS API and do a GET, and you get the same thing that anybody else would get. So you can debug the system using a web browser. It's pretty slick. So receivers, what does a receiver actually advertise in the registry? Well, it advertises that it's a video receiver or an audio receiver. It's pretty important. It advertises things like, what device is it a part of, and is it, the first audio channel, the second audio channel? There's ways to signal that kind of stuff. And then importantly, the receivers advertise how they're organized into their parent devices and parent nodes. Now, senders, same idea. A sender has, information about, is this sender the first audio stream, the second audio stream, the third, and also the video information, and again, how it relates to the devices it's in. So this is all just system organizing information that's part of the, what is a sender. And then senders, interestingly, have a pointer to this thing we talked about, saying we were going to talk about it, but we weren't talking about it yet, called a flow. What is a flow? Well, funny you should ask. So a flow is really meant to represent the content in the network. So if I have, say, a stream of video, I might have that same identical stream of video go into the network on two or three different addresses if it's a complicated network. So there might be multiple senders, but they point back to the same flow, where the flow has some details about things like what shape and size is the video, what color space is it in, if it's audio, what bit depth is it, how many channels, that kind of thing. So the flow has kind of that information. Equally, the flows have pointers to devices, and the flows have pointers to a thing called a source. You say, what's a source? Well, a source is an original piece of content. So a source is things like, if I have a camera on a set and it's pointed at the anchor and it's this camera is a source. Now, you might have a lot of versions of that camera flying through the network. You might have a UHD version and an HD version, and maybe a compressed proxy version. And those would all be different senders, and to the extent that they're different resolutions and things, they'd be different flows. But they're the same source. And the reason we use this source concept is so that you can tell that in some way, these are what we call editorially equivalent. So I can use any of them in a relationship of what time is a certain frame, or is that the shot that I wanted? But then ultimately, it's like proxy editing, and then the final melt uses the originals. You have the notion that they're equivalent for making edit choices, but they're obviously different qualities. So sources in the network or in this registry have, audio versus video, and they have, again, the device pointers, that sort of thing. Now, this ISO 4 is not just in the registry. Every device also exposes the same information from its own API on the device. So if you dial in the IP address of a device and you pull in the NMOS information that way, you'll get all the same data, In fact, the device is required to keep it identical. And then away you go. You can look at it there. And most controllers actually read it from the device because the device is, more reliable sometimes. There's obviously registry is important. So there's different mechanisms for redundancy of the registry. You can have two registries that are, different priorities, and everybody uses one until maybe it's not there and then they switch to the other. Or you can have multiple registries of the same priority, and devices will just pick one based on whatever mechanism they pick. And if that happens, you need to make sure the registries themselves are federated somehow. And most registry implementations do something like that. Now, that's all ISO 4. That's how you know what's going on. But we haven't switched to stream yet. And really the whole point was to be able to switch streams. So what happens in this ISO 5? Well, in ISO 5, you have controllers, where a controller is a thing that actually wants to switch signals. And you have senders and receivers that make and eat signals. And so what do the senders and receivers have to do? They have to respond to this ISO 5 API. And the controller has to know about the parts of the system and decide what it's going to do next. So when you switch signals, what happens? Well, you have a routing control system that understands names, like that camera's camera 3, or this playback server is, playback 5. And then it understands groupings, which audio and video parts go together to make camera 3 or playout 5. And then routing is done at that high level using names. But under the hood, a bunch of things happen, right? An operator says, hey, I want to switch signals, and the signals switch, and the operator gets status, and everybody's happy. But fundamentally, what really happens is that the control system uses ISO 5 to tell the monitor, hey, monitor 3, switch your video to this. Monitor 3 says, hey, I did that. And that's all done with ISO 5. And then down at the network layer, there's IGMP and other signaling that goes on down at the network layer to follow up on it. So again, if you're a human, you start reading this ISO 5 interface, there's a bunch of pieces, but it's fundamentally, it's an API on the media node. So it's not on the registry, this is on the media node itself. Later, the registry gets updated after a receiver changes, but it's used both, to do bulk operations and to do single operations, to just say, change this one stream. Senders, pretty much the controller can just read the sender, and it has this transport parameters list that's all the multicast addresses and things. And then there's another branch that offers the SDP. So there's the SDP, and there's like a typical URL of a NMOS device. So when you read it, obviously from the sender, it's just there's your SDP, and then you can use that SDP when you're controlling receivers. Now, receivers have an active endpoint that is, what's running right now, and a staged endpoint that says, what should I do next? And so a controller patches to staged, and then that becomes active. And if you read the active branch, you get what's happening right now, which has, again, most of that same looking data that was on the sender, plus the transport file woven in there. So there is your SDP object again. Active is always a summary of what's happening in the system right now. So can you build a system without NMOS? Well, of course you can. And we have built a number of systems without reliance on NMOS, but it's painful because in every project that doesn't have NMOS, or where devices don't have NMOS, we have to work with the vendor of every device to work out what protocol are we going to use. Do we have a driver for that? If we don't have a driver, we have to write one. And the same thing the other way around. As a device, if we're in a project that doesn't use NMOS, then we have to work with whatever the control vendor is to say, okay, here's our API, and explain it and all the things that are in it and teach them how to use it. And so it's a lot of work for everybody involved. But now that we have ISO 4 and ISO 5 as an industry, everybody's saving time and money, because our controller can use NMOS to talk to lots of devices, and there's a lot of control systems out there that can talk NMOS to control us. So it's actually working out quite well as an industry. Now, of course, there's other considerations. You might have non-NMOS devices in a project. And so you still need some drivers, even if most things are NMOS. You might have streams that you don't even have a driver for. You just know that these streams turn up. And so there's some work there too. But these are all standard problems in the control world. Ultimately, does NMOS solve every problem in the world? Well, no, but it solves two problems we care about a lot. How do you find all the parts of the system during system configuration and later? And how do you do at least enough endpoint control to switch streams reliably and to switch streams in a vendor-neutral way? So to sum up, NMOS is shipping on lots of devices today worldwide. From us, from other people, and most other devices that are worth owning have it on their roadmap. So if you're looking at a piece of equipment and it doesn't have NMOS and they don't want to have NMOS in the future, you really got to ask yourself why. The same thing is true on the control system side, that most major control systems have NMOS today or have it in their roadmap near term. And again, if your control vendor doesn't have NMOS and doesn't plan to have NMOS, you've got to wonder why. Because NMOS, ISO 4 and ISO 5 are making a difference today in projects worldwide. Now, if you want to learn more about NMOS or see it in action on various pieces of equipment, feel free to reach out to the Imagine sales staff, and we'll be glad to set you up with a demonstration of how ISO 4 and ISO 5 work in a multi-vendor ecosystem today. Thanks, and have a great day.